In our video on methodology, we discussed the similarities between real-world learning and machine learning. Basically, teaching by examples requires us to use some examples for the real teaching act, which is training, but to keep some of them apart from validating the learner and having a final test set to assess the student's proficiency. But a few questions still have to be answered. First, what is the best way to evaluate the learner? And second, what is the best way to separate and use our examples? Here, we shall focus on the first question. We want to assess the learner's proficiency in a way that is most accurate and useful. It's easy to see that different problems require different types of evaluation. Soon, with the autumn rains, these mountains will flourish with mushrooms. People will rise early in the morning to go in the woods and pick mushrooms for hundreds of different culinary preparations. This is Carla. She is very cautious. If she ever doubts that a mushroom is poisonous, she won't pick it up. She is so cautious, in fact, that she leaves on the ground more than 10% of perfectly eatable mushrooms, just because she has a little doubt about them. So her success rate is as low as 90%. This is Bob. He's very bold. Whenever he thinks that a mushroom is edible, he picks it up. He only commits one mistake every 1,000 mushrooms, collecting an inviolable 99.9% success rate. Would you trust bold Bob to provide mushrooms for your risotto? He makes much less mistakes than cautious Carla, but he makes them both ways. Once every 1,000 times, he'll provide a poisonous mushroom, whose effects might range from hallucinations to fatal liver failure. Not all errors are born equal. Suppose that you are a car maker, a high-end car maker, say a Ferrari. You produce 100 finely crafted cars in a year. Despite all your best efforts, 3 of these cars are defective. Your quality assurance team checks all cars, looking for flaws, but they can commit errors too, maybe because of a miscalibrated test tool or because they ate Bob's famous mushroom fricassee. Of the 3 flawed cars, they only blocked 2, while 1 passed their tests. Of the 97 good cars, 3 were considered defective and 94 passed the tests. What we have just drawn is a so-called confusion matrix where all tests have been broken up into 4 outcomes. The top left counts the so-called true positive cases, defective cars that have been correctly identified as such. Remember that our question is there a defect? So a defective item will be a positive case to us. In the top right, we count the false negative cases. The car was declared okay, but we were wrong. In the bottom left, we find the false positives. The QA team didn't pass 3 good cars. Finally, in the bottom right, we find the true negatives, good cars that passed the test. Note that the errors are concentrated in these 2 entries. The QA team had an error rate of 4 out of 100 cars. While 4% seems reasonably low, consider the effects of the 2 errors. On the top right, we have a defective car that has been shipped to a customer. A flaw in the car might harm the owner, and in some cases the producer might be forced to recall all 95 shipped cars for further controls, and will likely suffer a severe loss of reputation. On the other hand, a false positive just means that some more tests will be done before finally recognizing that the car is okay. In this case, a false negative is so expensive that one might just look at the first line and say that the QA team was wrong once out of the 3 important cases, that is 33% of time. This is the false negative rate. However, The QA team has a very simple way to achieve a 0% false negative rate. Just declare that every single car is defective. In this case, no customer will ever be harmed because of an undiscovered flaw. However, the QA team's error rate would skyrocket to 97 errors out of 100 cars. Another way to handle the different importance of false positives and false negatives is to assign a weight factor to them, counting each false negative case more than once. Suppose now that you convert your workshop from car making to jeans trousers. You make 100 pairs of trousers a day, and 3 of them are defective. Again, your QA team fails to identify a flawed pair, false negative, and incorrectly marks 3 good pairs as flawed, achieving the same 4% error rate as before. The customer who purchased the defective pair won't probably be killed by them. He'll walk back into the shop and change it with a good pair. On the other hand, the false positives mean that 3 perfectly good pairs will be discarded and destroyed at a much higher cost. If the cost of false positives is high, we might just look at the first column and see that out of the 5 times that a pair was declared defective, 3 were errors. The false positive rate is as high as 60%, meaning that 60% of capital loss in supposedly defective items could have been spared. If false negatives are not a big issue, however, your QA team might as well take advantage of the fact that defective items are rare and declare all items as good, thereby lowering their error rate to 3%. This is precisely what you would do if you didn't have quality assurance in the first place. However, we can't tell whether this is good or bad for your business. To wrap up, different types of errors can have different impacts, so there is not a unique way to measure them. When positive cases are rare, the error rate may improve by always answering negative, but this may not improve your business. Assigning weight factors can be a good way to handle these issues. Thank you for listening. You will find more details in our book.